So might as well finish this and then call it a day. So I talked about harmonics briefly by saying that you have a 60 Hertz fundamental frequency and then it's just multiple of that. How I'm trying to tackle this is I'll have an IN or a VN here, cosine 2 pi ft plus t. This is omega t, just keep in mind I just expanded that. And to bring in my different frequencies, I'm just going to use an n. So n can be 1, n can be 0, 1, 2, 3. If n is 0, then this doesn't make any sense because it's just DC here, 0. So we'll start with n is equal to 2, even number. We'll do n is equal to 3. I'm not going to do on this, tonight I'm not going to do n is equal to the other numbers, but on Thursday I'll cover that as well. So for the sake of simplicity, let's just go with I and probably an IM just to call it a current. In which case I have three phases. So my IA2, just to go with into, would be some sort of a phase current in RMS, angle 2 times 0 degrees, which is essentially some sort of a phase 0 degrees. And this should be clear from what we have been discussing so far, with IA being here, and I'm going with my IBC sequence, so nothing new here. $120 here with a negative, 120 here with a positive. So my IB2, if I go by the same logic, I phase 2 times negative 120. Keep in mind this 2 is coming from me introducing different frequencies. And what does this turn out to be? This turns out to be 240 degrees, right? Negative 240. Can you see that? Mm-hmm. 2 times negative 120 will lead to by phase 2, negative 240, which is equal to what?
Isn't it like positive 120?
Which comes to positive 120. So it just occupies the space which I had earlier reserved for IC, but it took the place of IC. So my IB gets rotated here. Now let's look at IC2, yeah. 2 times 120 degrees. $240 degrees, which is equal to what? Negative 120. And if I have three, beginning of class I heard a lot of vectors going around. It's a phasor. Please don't call this a vector. Vector has a magnitude and a direction. Current doesn't have a direction, so to say. It just picks up the easiest path and just flows through it. If I am standing on a copper plate, it's just going to go through the copper plate. If there's a silver plate next to it, it's just going to pick up the silver plate. So there is no real direction to a current, it just picks up whatever it wants. So this is a phasor. So what happens here? If I take IA2 plus IB2 plus IC2, I'll end up getting, I'm just pulling out the phase currents here. What was my first one? Some magnitude with an angle of 0. Some magnitude, and I say some magnitude because I just picked out this I phase 2 outside. 120 degree and some phase minus 120 degrees. And this should end up in the neutral and it should be 0. Tell me that I was
For the angles, I understand those, but the, I guess the magnitude, why do we simplify it to ones?
Or you could keep it the way it is. I could get this helps me putting it in the TI-89.
Yeah.
So just do this. Irrespective of what number this is,
Mhm.
do you mind checking this in the TI-89? 1 angle 0, 1 120 and 1 negative 120. Alright guys, I need to get the next frequency in and come to some sort of a logical conclusion. Now let's examine n is equal to 3. And again, the 3 is, I am going to do, I am cos, this n is what I'm moving to 3, just to keep my life easy. So n is equal to 3, I would end up with IA3, did I use IA2? Yeah, IA3. I phase 3 times 0 degree, which is I phase 3, 0 degree, IB3, times negative 120, and what's this guys? Simplified way. Negative 360, that's fine. Which is what? 0, thank you. So IB3 and IA3 are both the same currents. And look at IC3, I3, 120 degrees, 360, which is again phase 3. Now if I look at my neutral, which is, and I have to apply a KCL here, my neutral current, let's go with caps, is sum of IA3 plus IB3 plus IC3. I have 3 times I phase 3 angle 0, or 3 times IA3, or 3 times, sorry, IB3, or 3 times IC3. And this is a, as you need to tell me when I am out of bounds. Yeah. So you have Im cos omega t plus p, but to fool around with the frequency, I just put an n there. IA3 was 0. This is negative 120. Sorry, 3 times negative 120 and 3 times 120. So all of them end up being 3 times I phase angle 0, which means whenever you have odd multiples of frequencies, and we discussed about the odd multiples somewhere here. So if it's 60 Hertz, you're going with 180, 300, and 420. If you're looking at the even, it should be 120, 240, and 360. Keep in mind, I'm dealing with US frequency, US or Canadian frequency. So if you put an oscilloscope or a spectral meter, these just cancel away. It's like they just don't even exist. These guys will show up. So you not only have a sinusoidal wave, and I'll show you some pictures next time around. So imagine this to be a 60 Hertz. It's 3 times, right? So half will have 1.5. Now I'm going to mess this up, pretty sure. So I need 3 waves inside this.
That's hard.
So somehow I'm going to see 3 more waves here. And then, you know, what is it? 5? Yeah. Another one would be like 5 more. So honestly, if you see a bunch of sinusoidal waves, you are not going to get a lot of info, which is where your Fourier analysis is going to come into play. So you'll take your Fourier and you do a Fourier analysis of a sine wave, and then all that you're going to get is an x and y, and that's part of your lab at 60 hertz, 3 times at 180 hertz. What's the other one that I mentioned? 300, right? 60 times 5? 340. So you will see a big magnitude here. Depending on the problem, you might end up getting a higher magnitude for the 180. And this is voltage or current. Voltage or current that you are doing. And here you might get a small one. And here you might get even a smaller one. This magnitude simply depends on the kind of device that you have on the other end. And you would see that you are missing 120. So you don't see 120. You don't see anything on 240. They're just gone. Like the even ones are just gone. These frequencies are called triplets. It's an interview question. They'll just casually ask, hey, what do you think about the triplets? I've heard weird answers all the way from WWE. Guy was just confused with something else. I don't know what he was talking about. But I liked his guts, and I hired him, I can tell you that. So 60, 120, you're not going to see anything on 120, 240 you're not going to see. Multiples of 3, so 6 times 3, 18, 6 times 5, 300, 420 and whatnot. My capstone was based on this, and we had to pick up, I think, up to the 10th or 15th harmonic, I believe, and we checked a lot of stuff, and that was my capstone. So that's more or less the lecture. One last thing, and I'm going to let you guys out of here.
Nice.
And those of you who just want to head out now, please feel free to head out now. I just want to show you a bunch of pictures, and then we are done for the day.
Okay.
I'm not showing you.
Okay. Those pictures.
So, a week from today, yeah, exactly a week from today, we will start with, can you guys see this?
Yes.
We're going to start off with transformers. I intend to show you a smaller transformer, but this is a giant. This fence is the fence that I was talking about with 10,000 volt DC to keep the squirrels out. This would be yay big, maybe. So you can feel like how big this thing is. Today it takes about 3 years for us to place an order and to get this because it is highly customized. Used to be about a year and a half, but not these days. It takes about 3 years. Don't need to know this, but this is how we regulate the voltage. It's literally called a voltage regulator. Used to be an off-the-shelf, like you place an order, once they see the money or they know confirmation, they'll ship it out. Last I heard is like 10 months. So everything is today. And every transformer has certain capacity. And when we start with the low end of the capacity, but as we get more Teslas into our system, it's 3 years out. A bunch of people are buying their Teslas. So the way how we increase the capacity of this transformer is the same way that if you are a gamer, or you guys add a bunch of heat sinks, right? To increase the speed. Same thing. We keep on adding fans here. That's the easiest way to cool this guy down and kick up the MVA. So right now I'm working on a project where it's 22 MVA, so mega. I'm getting it to 28 MVA. And it was the coolest project. Today evening I told, hey, there's a rush. Summer is coming and we'll need it. I'm like, yeah, big deal. So we keep on adding fans, and there are different other methods. Yeah, that's the fans. You guys saw a breaker where you guys calculated a small breaker, right? 40 amp breaker. This is the breaker that's being used at a substation. I would be, so this handle is a high height here. So yeah, pretty big, so to say. I'll be somewhere here. Maybe I'm way tall to the nameplate. So that's the size of breakers that you're dealing with. And here, you're not dealing in amperes, you're dealing in kiloamperes.
Wow.
You do not want to be near this when this goes bad. It's just a blast and yeah. Don't want to get into that.
Do you get charred, or is it still like survivable?
Yep. Physical force.
So this is an outdoor one. See, here's how you should think of it. When there's a blast or any kind of explosion, how quickly can the energy disperse? This breaker is not considering that a human is standing here. Across this, there is enough air that it will explode and try to come to a stable situation. Today, because land is so expensive, no one wants an ugly substation near to their property. We are putting it in an enclosure like this. And think about this. In this space, there's a term called arc flash. That's the entry level blast, arc flash. And you see a lot of stuff, but that's like an entry level thing. You guys are not going to see this. Let me see if I can. So our main breaker, and this is just to supply our receptacles. It's not even the main one. It's 225 amps. That's the small receptacle that we use. And our yard lights and whatnot, like the HID lamps that you guys did, it's like 100 amps. Can you see 100 amps on the screen?
Yeah.
Yeah, 100, 50. And each of these breakers, similar to, we calculate the current, we do a 1.25, and we figure the next possible breaker. So each one has to be done. Fortunately, there are a lot of yeah. That's all that I had for. That's all that I had for tonight. So, next class we go deep into harmonics, and then I'll come up with 2 formulas. Watch out for those formulas. Write it in your cheat sheet. Here's the way to think about midterms. 4 weeks. Each week 1 question. So that's like 4 questions. So that's about your midterm. And you have a sample midterm on Canvas. Download and look if you can solve at least 1 problem. One of the problem is literally the kind of problem that we solved at the beginning of the class, where you have a 480 volt or a 600 volt, and then you have 4 or 5 loads. So,
Cool. Thank you.
I want to ask